So what we have here is some closed curve. And a set of contours within this curve. It's in 3 dimensions. Okay? So any curve, any surface, I mean, in 3 dimensions that's bounded by this curve. Okay? So, curve C let's say a simple closed curve. This means a curve that doesn't intersect itself, making it simple. Closed, it comes back to wherever it starts from. So at any point, you go around the curve and get back to that point, staying on the curve. Okay? And it bounds a surface I'll call S. Really bad looking S, but we'll live with it. Okay? Okay, surface bounding, curve bounding surface S. Current. Total current I. Penetrates the surface S. Okay? Then the integral of the magnetic field around the curve is proportional to I. Okay? I'm just going to say it's proportional to I for right now. It's just a multiple of the total current that penetrates the surface. Okay? And of course, this proportionality involves K prime.
What ds is the derivative of the surface S?
The what now?
What is ds?
You mean the integral?
Yeah. Yeah.
Well, it means, yeah, I was going to say that. Let's say it. Okay, so you got a magnetic field around here. So you have total current I penetrates the surface. Okay? I'm not going to try to draw that. I'd have to get all artistic. Okay? That induces a magnetic field that could have various directions around here. Okay? And on any segment, let's say you have a segment here of the curve, and you don't have to worry about the details of setting up a line integral, which is what this is. I just wanted to tell you what it means, okay? One of you knows about line integrals. You just got to parameterize the curve, which you learned to do in second semester. You're learning that in second semester calculus, right? Parameterizing curves?
Yeah.
Yeah. So if it's a curve you can parameterize.
That wasn't convincing.
I was not convinced. No, but no, we did.
I think actually we're doing like parametric.
Well, let me just give you an example, okay?
He's not so big.
Yeah.
Yeah.
Oh jeez.
Very simple. C is a unit circle in the XY plane.
Yeah.
then you can parameterize that in many ways.
Yeah, it's just parametrics.
That would be a typical parameterization.
Yeah.
Now they can get a little nastier than that. It's an ellipse, then you put two different numbers in front of these and you get an ellipse that's elongated in one direction. If it's a rotated ellipse, you just give up and go do something else, okay? No, you probably have to look that one up, okay? But just a simple transformation, a little linear algebra, you can easily rotate an ellipse, okay? So what you do is, what do you partition? You partition the interval from 0 to 2 pi. Make sense? Well, if this was a circle, which it isn't, but you have, say you parameterize this in terms of t, here's your ith interval. So you plug in t sub I minus 1, you get this point on the curve. You plug in t sub I, you get this point on the curve, and you have a resulting displacement here, right? Make sense? So you have a displacement, use fancy colors. So you get a delta S sub I. Okay? So like if t is, ti minus 1 is 0.8 and ti is 0.9, then you plug in 0.8 for the cosine, right? And you plug in 0.8 for the sine, and that would give you a point. Okay? And then you plug in 0.9 for the cosine and 0.9 for the sine, and you get another point. Well, those would be the 2 points on the curve. Okay? And your delta S would be the vector from the first one to the second one. It's not particularly difficult, but we're not, I'm not going to ask you to actually do that. Just get the principle, okay? And it's worth understanding in general terms what I'm talking about, because you're going to have to do it in multivariable calculus, okay? And it'll give you a little head start to have talked at least about conceptually what a line integral is, and then the details of it, well, that's really all it is. Once you get the parameterization, Elam will tell you it's fairly straightforward. You might have forgotten it since the last time you did it, but it would come back to you very quickly if you have, okay? And there are details, but once you understand the concept, the details are relatively straightforward. You just got to remember them, and it helps, again, to know what you're doing. So what you have is you have this, and this would be your magnetic field. B at xi star, yi star, where that's some point on the curve, okay, inside this interval. So now you've got a magnetic field and a delta S. Choose the interval small enough that the magnetic field doesn't change by much, and also that there's not a whole lot of curvature, so the delta S is pretty much in the direction of any segment within this little segment, okay? So you have to use pretty small delta S's. That wouldn't help. A delta S this big wouldn't be a lot of use up here, would it? Because you got big changes in the direction, okay? So delta S could cut from this point to this point and totally ignore everything that happens in between. Well, you just then take B dot delta S. So this is the sum of your B sub I dot delta S sub i's, which approaches this interval. So, I didn't call this B sub I, but this is what I'm going to call B sub I, because I don't have room down here to write the X sub I star, Y sub I star. Okay? This is just a point within the interval. This is the vector displacement on that interval. We do the dot product, which just means, in this case, it'll be pretty close to the product of the magnitude of B times the magnitude of delta S, because the cosine of this angle here is pretty close to 1. And of course you want to understand the cosine well enough to visualize the fact that when the two vectors are nearly parallel, then the part of this vector that's in this direction, being the product of this magnitude and this magnitude times the cosine of theta, is pretty close to just the magnitude of this times the magnitude of this. Wouldn't be true up here. This is almost perpendicular. If you had a delta S up here, most of your B would not be in that direction. Okay? So anyhow, you sum those up, and there is a dot there, but it almost looks like it's part of the dot on the I, so you want to be careful. So we have this, okay? Now we'll worry about what the proportionality constant is. That's just a constant, okay? But we want to see how this applies, let's say, to this, okay? And this can be modeled as a series of coils, but it can also be modeled as a solenoid. So let's talk about what a solenoid is and how you calculate the magnetic field, because once you know how to calculate the magnetic field of a solenoid given the current, then you can figure out the inductance and do all the stuff we've been doing with inductance, okay? You've approximated inductance if you've done everything I've asked you to, which nobody ever does. And for just a loop, you just take the current or the magnetic field at the center and assume it's through the whole loop, okay? From that you can deduce how the rate of change of the current is related to the rate of change of the magnetic field, which is your back EMF, okay? And that ratio is just your inductance.